Hello, linear algebra friends. This is Professor Gibbons with yet another example of spanning sets. So in this example, I want to look at our normal, friendly R3 vector space with the usual addition and scalar multiplication, and I want to know if this set S with these three vectors, v1, v2, v3, as written, spans R3. So does this thing span R3? Well, I already know that S is a subset of R3 because those are three vectors that are in R3. And we've got a theorem then that tells us that the span of S is a subspace of R3 and hence a subset of R3. So all we really need to show, if we want to show that R3 is spanned by this set, is that R3 is contained in the span of this set S. Well, what does that mean? We want to take an arbitrary vector in R3. So let's look at ABC. And we're trying to find these real numbers x, y, and z so that we can write ABC as a linear combination of v1, v2, and v3. That is, ABC should be x times v1 plus y times v2 plus z times v3. And if I've got that, let me look at my vectors again. All right, well that tells me that x times 1, 2, 1 plus y times 1, 0, 2 plus z times 1, 1, 0 should add up to ABC. Now, we've got a theorem in our pocket that has a lot of utility for us. That theorem is the matrix vector product theorem, the MVP, and I'd like to give you an idea of how to set ourselves up to get the MVP going for us here. So if I think about x, y, and z, can think of those as the entries of a vector of variables, x, y, z. And then I can think of these three column vectors as the columns of a matrix A. Now, if I look at this and I let my MVP bell ring in my brain for a little bit, I see that what I get is 1, 2, 1 times x, and then 1, 0, 2 times y, and 1, 1, 0 times z. And so I've got the columns of this matrix on the left here times the entries of this vector. And luckily, we know a lot about how to solve a linear system like this, right? We set up an augmented matrix. Thank you, MVP. That was super clutch that you came in and saved the day for us. So we're going to set up our augmented matrix, right? We're looking for solutions to the system A times x equals our vector from R3, which is ABC. So we are going to row reduce. Now, I will warn you that I did all of the following row reduction by hand, so I checked one entry at the end of this, and I leave it to you to check the others. But assuming the row reduction went appropriately, you'll get the gist of how this works. So let's go ahead and do some row reduction. All right, here's my augmented matrix. I'm going to take row 2 minus 2 row 1 to row 2, and row 3 minus row 1 to row 3. So I'm getting rid of the the initial entries in those two rows. When I do that, the first row stays the same, and I zero out the first entries. And I need to remember to do this to my ABC vectors, or vector on the other side as well. As I was blabbing at you, I did this other row operation. So I took 2 row 3 plus row 2 to row 2. So that gets rid of the second entry in the second row. And when I do that, I do the corresponding row operation to this, the second entry of my ABC vector. So I've got kind of a mess happening over here. And I'm just going to continue row reducing on my merry way. So let me get that, that negative 3. I'm going to turn that into a 1 by dividing by negative 3. And then I'm going to zero out that bottom row, the last entry in the bottom row. Okay, and I do a bunch of related row operations to the other side of my augmented matrix. It's starting to look a bit disgusting. Anyway, through the power of ... I end up with the identity matrix on the left and this kind of weird-looking vector on the right. And what I have is that these things are solutions for x, y, and z. So negative 2a plus 2b plus c, that's my x vector. A minus b plus c over 3, that's my y vector. Sorry, my x vector, I think I forgot to divide by 3 verbally. And then my z vector is 4a minus b minus 2c over 3. So that tells me exactly what x, y, and z values I need to plug in to cook up my vector ABC, right? So I'm going to take negative 2a plus 2b plus c all over 3 times v1 and so on and so forth. I add these things up. Now, I wanted to check that my row reduction wasn't too far off. So what I did here was, let's just see that the third entries with these coefficients are going to add up to c. So I'm going to take my coefficients times 1, 2, and 0. Make sure that I get c at the end of the day. That's what I'm doing in pink over here. And yes, my third entry adds up to c because I have c over 3 plus 2c over 3, and that is in fact c. So I leave it to you to check my other entries. Well, what does this mean? We were asking whether this set of vectors, v1, v2, v3, spanned the vector space R3. And what we found was that if we start with an arbitrary vector, ABC, we can cook up the coefficients we need to use those vectors to write ABC as a linear combination. And that says for us, yes, the span of this weird set S is indeed R3. Now, how do you know if you're not going to be able to span R3? Let me show you that. I have one more little slide here to go. So if we were row reducing and we got down to something with a 0 row, but the stuff on the augmented side where we put our ABC solution ended up having something like, I don't know, a plus b plus c, this tells us there are certain vectors that we can't span, because that last row, if you think about what it's saying 0x plus 0y plus 0z should add up to a plus b plus c. And the only way that works is if a plus b plus c is equal to 0. So that means we can't span vectors like, I don't know, 1, 0, 0, or a vector like 2, 3, 1, because for those vectors, the sum of the entries is not 0. And that tells us that we have set up a linear system that is inconsistent for vectors whose entries do not sum to 0. And that means that we can't span all of R3. We can only span vectors in R3 where the sum of the entries is a plus b plus c is 0. And that's kind of an interesting way to think about what different types of row reductions and the different reduced row echelon form matrices you get tell you about the types of vectors you can span.